All right, guys. Mr. Jenkins here. Today we're going to start the kind of the last part of the second unit of Chapter 4. Kind of getting into definitely a new idea, and which is talking about the set of complex numbers. So far, everything we've dealt with in math, I believe this is true, has been real numbers. So we deal with lots of real numbers, rational numbers, and then even irrational numbers. But then we even get into this new thing, imaginary numbers. So first of all, that kind of sounds made up, but why do we need imaginary numbers? So right here it says consider the square root of negative 25. And we've always been told you can't take the square root of a negative. And that's makes sense because nothing squared is equal to negative 25. Our first thought is if we take negative 5, square it. Let my computer get caught up here. Then that would be negative 25, but it's actually 25, right? So for this reason, we start to use this imaginary unit, I. Okay, so I is equal to the square root of negative 1, right? And so I squared is equal to negative 1. So we're going to use that fact to simplify some of these. All right, so number 1 is pretty simple. So the thought here is we break it down into the square root of negative 1 times the square root of 36. So this is equal to I. This is equal to 6. So I times 6. We write that just like we would like a coefficient of a variable. We would say 6. All right, so I'm just going to do a few of these. Sorry, the numbers kind of are weird. We go from 1 to 4. I'm not really sure what happened there. Formatting thing. So next one, thinking about the square root of 50. We could break that down into 25 times 2, thinking about perfect squares. So all together, we would break this down as the square root of 25. That's a perfect square times the square root of 2 and times the square root of negative 1. So that's 5 square roots of 2 times I. 5 square roots of 2i. Or I guess, sorry, the way they put it and the way it's on my notes. I guess we put the I with the 5. Sorry about that. Either way, it means 5 times the square root of 2 times I. So I guess the way that properly formalized would be 5i square roots of 2. Order doesn't really matter though. Okay. I'm going to leave number 5 for you. Let's look at number 6, maybe. All right. So on this one, breaking down the square root of negative 8. So that would be perfect square that goes into that would be square root of 4. So we have square root of 4 times square root of negative 1 times the square root of 2. So all together then that would be 2i square roots of 2. So then we have 3 times that, 2i square roots of 2. 3 times 2 gives me 6. So final answer here would be 6i square root 2. So all this seems kind of weird, but I think you get used to it as you go. All right, let's look at number 7. Okay, so the first thing I think that would be wise to do here would be to actually, I think here's where you could get confused on this one. Okay, so the thought might be this is equal to the square root of negative 2 times the square root of negative 6. But you can't do that. So the square root of 12. So that's not going to work. Here you have to take care of these square roots of -1 like by themselves. Okay, so we wanna simplify this as kind of I square roots of 2 times I square roots of 6. Okay, so then we put these together, and that would be I times I would be I squared times the square root of 2 times 6 times the square root of 12. Square root of 12 can be simplified as square root of 4 times square root of 3. So I squared, all right, this is the first time we've seen this. I squared is equal to -1, right, because it's the square root of -1 squared, right? So that's -1 times 2 square roots of 3. So that'd be -2 square roots of 3. And again, like, you know, think about if we would have done that first step. If we take the square root of -2 times -6, that'd be the square root of 12, which does not give us -2 square roots of 3. That would give us 2 square roots of 3. So that would have been incorrect. I'm going to leave number 8 for you. That's kind of a tough one, all right? But it's kind of like number 7. Let's skip ahead to maybe... let's do maybe a couple more of these. So, I don't know, let's do maybe number 10, okay? Look at number 10. Let's take 7 times 3 times -2, so that'd be -42. And then times I times I times I. That'd be times I to the 3. All right, so what do we do with that I to the 3? Well, we kind of break it down into I squared times I, right? Into quantities we know how to deal with. So we have -42 times I squared times I. Right, so why'd we do that? So now we know I squared is equal to -1. Okay, so this just says -42 times -1, so that'd be +42. And then we still have that. Okay, so I'm going to leave the rest of those for you. So I suggest you try them. So just to recap, we did not do 5, 8, 9, 11, or 12. Those would be good extra practice for you guys to do and check them. Okay, I would say a good resource for this, as long as you don't overuse it, is I like kind of checking my answers, since this is kind of a abstract idea. I like using the website Symbolab. They have a complex number calculator where you could type in, say if I'm doing number 8, I could type in 3 square root -10 times 4 square root -3, and I could check my answer. Okay, I wouldn't lean on it too much, but that's another good resource. All right, so the complex number plane. All right, so this kind of gives you a graphic representation of what we are doing when we are talking about complex numbers. Okay, I'm going to skip over this and just show you. It's a pretty simple idea. All right, so if it says plot the complex number and find its absolute value. Okay, so if I'm going to plot this, and it goes into why this is just like the ordered pair 5, -3. Okay, so that'd be 1, 2, 3, 4, 5 to the right, and 1, 2, 3 down. Okay, in other words, this is my real number axis. This is my imaginary number axis. Together, they make a complex number. All right, so 5, -3, and then its absolute value. So what does that mean? That just means its distance from the origin. So basically, we're finding what's the distance of this. All right, and basically for that, we just use the distance formula. Okay, so that would be the the square root of 5 squared plus negative 3 squared, or you could just do 3 squared. So that'd be the square root of 25 plus 9 would be 34. And then you'd want to break that down if you could. 34 breaks down to 17 times 2, so you can't really break that down or simplify that. So its distance is the square root of 34 units, right? So this is a pretty easy question to work out as long as you know what you're being asked. All right, so finishing up kind of with complex number operations. Going to look at a little adding complex numbers and then subtracting. First thing that's important on number 1 is recognize that it is an addition problem, right? So really this is the same as if it said 3 plus 4i plus 7 minus 5i. Okay, I just dropped the parentheses, right? And then all you do is you just combine like terms, okay? So you have 3 plus 7 is my real part, so that'd be 10. And then 4i minus 5i as my imaginary part to come up with the complex number 10 minus I. Or to take it back to the coordinate plane, that'd be like the coordinate 10 comma negative 1. All right, so I'll let you do number 2. Number 3 is a little different because here you need to distribute that negative. Okay, so this one is like 7 minus 6i minus 6 plus 10i. All right, so be careful if you have a minus sign. You got to distribute that negative. Combine your like terms. 7 minus 6 is 1. Negative 6 plus 10i. Negative 6i plus 10i is plus 4i. So addition and subtraction is pretty simple. Let's go ahead and look at the multiplication. So number 4 is another subtraction problem. Might have you look at that one. Multiplication is just like a binomial times a binomial, right? So all we're going to do is distribute twice. So we have 5 times the quantity 4 plus 6i, and then minus 3 times the same complex number. Okay, so just like if it said 5 minus 3x times 4 plus 6x. You do the same kind of math, right? And then we'll combine like terms at the end. So distribute the 5, we get 20 plus 30i. Distribute the minus 3. I wrote 3i there. Plus 30i. Distribute the negative 3. We'd have minus 12 minus 18i. Okay, and then again, we combine like terms. So 20 minus 12 is 8. That's my real number part. 30i minus 18i is plus 12. And that doesn't match up with my answer, so I'm trying to see what I did wrong here. Oh, okay. Sorry about that. Did mess that up. Glad I had my notes here, or I wouldn't have caught that. Try that again. And then we take the minus 3i times 4 plus 6i. So negative 3i times 4 is minus 12i. Negative 3i times 6i is minus 18i squared. All right, now remember that I squared at the end that's a real number, right? I squared is equal to negative 1. So that'll be a thing you'll tend to forget until you practice this a little bit. Okay, so really this last term is negative 18 times negative 1. All right, so as we simplify, we'll keep that in mind. So my real number part is 20, and this is minus 18 times negative 1. So really that's plus 18, right? So 20 plus 18 is going to be 38. Then my imaginary number part, I have 30i minus 12i, which would be plus 18i. Number 7 is as simple as it looks. You're just distributing a minus 7i. And then let's do maybe just number 9. Actually, let's look at number 10. I'll leave number 9 for you. So that says, I kind of wrote over it, but it says 3 plus 5i squared. You would just have 3 plus 5i times 3 plus 5i. Okay, I want to look at number 10 because that leads into our next example. Okay, so this one is a 4 plus 2i times a 4 minus 2i, right? That should look somewhat familiar if we think about binomial times binomial. So let's just go ahead and do it. So we have 4 times 4 minus 2i. Screen get caught up here, and then plus 2i times 4 minus 2i. All right, so then we distribute. 4 times 4 gives me 16. 4 times minus 2i gives me minus 8i. 2i times 4 gives me plus 8i. And 2 times minus 2i gives me minus 4i squared. All right, so what happens here is we can see that minus 8i and plus 8i are going to cancel, right? And then we end up with 16 minus 4i squared, right? So this is like this is kind of like a difference of squares, right? Difference of squares, we end up with perfect square minus perfect square. But on this one, remember that perfect square at the end, that's a real number, right? Because that's negative 4 times negative 1. Right, so all together, when we combine our like terms, we have 16 plus 4 is 20. So this is a big deal right here, right? So this is what we do to basically take a complex number to a real number. All right, is if we multiply an a plus b times an a minus b or vice versa. Okay, and you know it's important when they have a special name for it, right? So numbers in the form a plus bi and a minus bi are called complex conjugates. All right, so we will finish out the day 1 notes, and I know this is kind of a long set of notes for day 1, but this will lead us into day 2 pretty nicely. All right, so the directions here says to simplify a division problem or a fraction with complex numbers, multiply the numerator and denominator by the complex conjugate. In other words, you cannot, you can't have an imaginary number in your denominator, right? That's what you got to get rid of. Okay, so looking at number 12 is kind of a weird one to start with. But you could do this one in several different ways. Actually, let's come back to the ones like number 12. Let's focus on 14 through 17. That's more like what you would have to do on a test. All right, so you would have a complex number in our denominator, right? We don't want that. Your directions on a test would just say to simplify, okay? So to simplify, we want to get rid of the imaginary number part. All right, so that's an a plus bi. So we want to multiply by a minus bi. So 3 minus 5i. Right, and then anything over 1 is itself. So that's why we aren't really changing the fraction. Okay. So on the top, it's pretty easy. All I'm doing is distributing. 7 times 3 is 21. 7 times minus 5i is minus 35i. On the bottom, though, you'll get used to it. I'll go ahead and show it, but we'd have, 3 times 3 would be 9. 3 times minus 5i would be minus 15i. 5i times 3 would be plus 15i. And then 5i times minus 5i would be minus 25i squared. But ultimately, we just want to be able to remember this, right? When I multiply a plus b times a minus b, I just get a squared minus b squared, right? So 9 minus 25i squared. A squared minus b squared, right? It's like a difference of squares. So that's 9 minus 25i squared, right? And then we have to clean that up. That really means 9 minus 25 times negative 1. So 9 plus 25 would be 34. Okay, and that kind of, if you go back to our graphing example, right, this ends up being just like the distance formula. Okay, if we plotted that, that'd be on our complex plane. Either one of these, that'd be 3, 5, right, and its distance would be 34. So that ends up being your denominator, right? That's a shortcut that ultimately you want to remember, or else you're going to have to do all this extra work every time. Okay, let me just do one more because I know that's a lot. I'll go just a little bit quicker. So let's do 16. So my denominator here is an a minus bi. So I want to multiply. My complex conjugate is 3 plus 4i. Sorry, there's that delay. So I'm multiplying by 3 plus 4i over 3 plus 4i. I'm going to use my shortcut on the bottom, okay? So I know it's going to be a squared minus b squared. That's going to be my denominator, right? So that's going to be 9 minus 16i squared. That's what I'm going to get on the bottom. Which hopefully you're thinking ahead, that's really going to be 9 plus 16, right? So 25. All right, there is no shortcut for the top, so we'll just have to go ahead and multiply it out, okay? So 2 times 3 is going to be 6. 2 times 4i is going to be 8i. 7i times 3 is plus 21i. And 7i times 4i is going to be plus 28i squared. 28i squared. All right, so I'm going to go ahead and clean that up before I write it out. So my real number part is going to be 6 minus 28. Remember, that's 28 times negative 1. 6 minus 28, so that'd be negative 22. And then my imaginary number part is 8i plus 21i, so plus 29i. All right, so then we clean it up. We said on the bottom that is equal to 25. So I believe they want how they want this on MathXL is you go negative 22 over 25. And then that last part is plus 29 over 25. Sorry. 29 over 25. So you can try it like I did. Let's see what that number was. Try to enter it like I did number 14, but I think they'll want you to split that up as 21 over 34 minus 35 over 34i, okay? Which is how it says it on the notes. So I know you guys are going to have questions about this. I hope you ask them because this is a new kind of abstract idea. I just threw a lot at you. but ask those questions and do what you got to do to understand this stuff. It's new. None of us have had this before, so feel free to ask about any that I skipped over. And hopefully you work hard on this and try to understand it. Thanks, and have a nice day.